Okay, guys, so let's start. So in this chapter, I'm gonna teach register, counters, and memory. Okay, these are main components we use them in any digital system. Uh, let's start with I already for counters. I already teach in sequential circuit. We designed already designed the counters. I'm gonna elaborate here a little bit. Anyway, so let's start with register. What is register? Okay, look here, guys. Let's start with flip flop. As I told you before, a flip flop is. Can anybody tell me what is flip flop? How can I explain it? Flip flop is a storage unit. You have to start with the word storage unit that can store 1 bit. That's it. Flip flop is a storage unit that can store 1 bit. Now, what about register? If you have, for example, n-bit register. N-bit register is a storage unit that can store a number of n bits. What I'm saying? So n-bit register is actually a storage unit that can store a number, this number of n bits. That's okay. So, and actually, if we have n-bit register, as you will see right now, in order to create n-bit register, I need n flip-flop. Makes sense, right?
Because my number has n bits.
Every bit, I'm going to store it in one flip-flop. Is that okay?
But you need to be careful here.
I don't want to misunderstand what I said. Yes. For example, if n is 3 bits, okay?
This one number.
These 3 bits are going to be stored in 3 flip-flops. That's okay. So here I have 1 bit here, 1 bit, one bit here. All of this is a register. Is that okay? But what you need to be careful about here is
this is one number. I'm not talking about
individual bits.
when you read, I have to read the whole number. When I write, I have to read the whole number.
Yes, this number is composed of bits, which is okay, but it doesn't make sense to just read individual bits because this is one number. That's what I'm repeating. Okay. So anyway, so this is a register. We use registers in any digital system all the time. Why? Why we? Any question about? Do you understand what is register is? It's like a flip flop, but flip flop.
You can say
flip flop register can still 1 bit. We don't say it this way, but it can. So here, a register is a storage unit that can store n bits. Is that okay? And actually, we use it all the time. If you look at any digital system, you will find something like that. If you have something like 4-bit parallel adder, this circuit needs 2 inputs. These 2 inputs are usually stored in 2 registers. Okay? Again, I told you the purpose of this course is not teaching a digital system, but I'm going to teach you the components that we use to create a digital system. Okay. But in order to understand how this component is useful, I'm going to give you some idea here. If you see any digital system like a computer architecture or something like that, you will see there are a lot of registers inside microprocessor. There are a lot of registers. Okay. These registers, as you see here, for example, if I have a hardware circuit doing other, in this case, I have 3 registers. For example, I here 1 register number A, I have another register to number B, and then the register as well. Okay. Any questions? What I'm going to do right now, I'm going to show you how can we design a 4-bit register. Okay. And as I told you, in my email, if I ask you a question, I will tell you to, I will ask you to draw n-bit register. In here can be 5. And here I'm going to teach you for 4. In exam, maybe I ask you for 3-bit, for 5-bit. So for sure, if you know how to do 4, it will be easy to do anything, any number of bits. Okay? But let's see, and then let's see how this register looks like.
as a block. Like a block.
We have here a register this way. this register should have a clock. It have a clock here, and then this is the output. For example, this is a 4 bits. So this is the stored number. For example, if you have 1100, so this register is storing 1100. Make sense? Also, this register should have 4 inputs as well. For example, if I put here in the input 1100, okay? So that means when the clock comes, the first, every time a clock comes, for example, if this one works for rising age, so every time there is a rising age, whatever you have here will be stored here. Okay? So that means this is the stored value. This is the number stored in the register. This is what I want.
So, okay.
So once you put a number here, this number is not gonna appear here immediately, but it's gonna all the time. When there is a rising age, this number will be stored here. Make sense? Okay. So how can you design this one? Very trivial, very easy. So the way you can design it here is, as you see here in this picture, here we have, because it's 4 bits, I need 4 flip-flops. I'm going to use D flip-flop because it's very easy. D flip-flop, I will use it. Number 1, you can see the clock is connected to all of them. All of them have connected to clock. This is number 1. Number 2, this is the stored value. This is the output value. This is the here. This one here, the value stored by the flip-flops. These are the values stored by flip-flops. Here, the input of these flip-flops here, this is actually the value here to be stored. When the clock comes. And how it works is very trivial. Nothing is new. Every time you have a clock rising age, this is how the flip-flop works. Whatever you have here is gonna come to here. That's it. You understand what I'm saying? So if I'm storing this number like 1100, and in the input I put 0000, something like that, or there is 1 here, when the clock comes, whatever you have here is gonna automatically stored in the flip-flop this way. Okay. You can add if you want, you can add a reset this way, a reset. Okay. If I add a reset this way, I'm gonna have the capability to reset the register at any time. If I want to reset the register at any time, I'm gonna just put 0 here. Once I put 0 here, I can clear it, 0 it. You understand what I'm saying? So that's what I'm telling you. In the exam, if I ask you about this part, I will tell you, please draw a 3-bit, 5-bit, 6-bit register. You understand what I'm saying? It's very easy to extend it. This one is 4 bits. So if I ask you to make it like 2 bits, so you have to stop here, 2 bits, okay? If I ask you to make 3 bits, gonna be here. If I ask you to make 5 bits, you can add 1 more flip-flop, and it's not difficult. Just nothing is new, right? I'm just using a G flip-flop, okay? And this one now becomes like 1 unit. That's why I'm telling you, you need to be very careful here. Yes, I'm using 4 flip-flops, but it doesn't mean I'm gonna read individual bits. No, it's
one number.
I'm gonna be stored in 4 flip-flops, but I'm gonna deal with this number in 1 unit. Every time you run, yes, internally they are stored in individual flip-flops, but I can't manipulate only one of them without changing others. Okay, so you need, when I write all of them or read all of them. Any questions about register? Yes, sure.
What is the R value?
R here, remember when I explained the flip-flop, I told you it's like an optional. Some flip-flop have 1 input for reset, and sometimes they have 1 input for preset or set. And these two are used for initialization. And sometimes you have a flip-flop without them. This is something optional. I can design it with them or without them. Here, I put them here to give you the capability of clearing the flip-flop at any time. At any time, if you want to clear it, clear means you store 0, 0, 0. Okay. At any time, just to put 0 here. Any questions? Okay. Now, I'm gonna do little bit modification on this register to add 1 more functionality. So what I want to do here, guys, I want to add 1 more input. This 1 more input, I'm gonna call it load. This is actually like enable or disable. Okay? It means if load is equal to 0, so this value is not gonna change at clock. When clock comes, you are not gonna update the value when load is 0, like enable and disable. Okay? When load is equal to 1, so when the clock comes, now you are allowing to write the register. You got what I'm saying? By the way, you can notice in this course, in many places in this course, we like the idea of adding enable and disable. Okay, this is something we like in any digital system. Why? Because when you see any digital system, we have what we call a control unit. This control unit is actually controlling all the devices in the system. Okay. So, for example, it's connected to the other, it's connected to the multiplier, it's connected to all registers, decoders, it's connected to everybody. It's a control unit. This control unit should have a capability to enable or disable any device because it's control. Need to control. You understand what I'm saying? So what I'm saying, that is why we like always for any device, we like to have like enable and disable, because this is something based on the instruction. Based on an instruction, this control unit is executing. For example, I need this register to change the value here. So here I'm gonna say to load 1 to enable writing. Okay. Anyway, so let me summarize what I said. What I said, guys, I'm gonna modify this simple register to add 1 input. We call it load. So this load is like enable. If load is equal to 0, when the clock comes, nothing. So this input, I'm not going to change this value. So the input is not going to be written because you are disabling it. Okay, you are not allowing load. Okay, anyone? Now, if load is equal to 1, if load is equal to 1, so in this case, once the clock comes, yeah, whatever you have here is going to be written. Any questions? Yes.
Would you just and the load and the clock together?
That's a very good question.
Yeah, very simple way to do it. Very good question. A very simple way to do it is actually you can do and. Here I can put here load, and then I put here the clock. Okay, so that when load is equal to 0, I'm gonna have here 0, and because there is no clock, so whatever you have here is not gonna be written because there is no clock. Okay. If I put here 1, so I will have a clock here. So by this way, I can use load as enable or disable. Very good question. Okay. The answer is yes, you can do that. However, sometimes we don't like to use it this way. You know why? Because this will affect, or it's going to have some bad effect on synchronization. Why? Because there is a delay here. There is a delay here. Okay. So synchronization means all of them is going to act at the same time. What happens here because of the delay of this AND gate, for example, if you have a rising edge, all of the system has 1 clock, as I told you before. So all of us are gonna act at the same time, except here, this one will be delayed a little bit. Some nanosecond or microsecond, sometimes this stuff. If it's not a problem for you, yes, you can make it this way. But you need to keep in mind, you are gonna lose some synchronization here. Okay? But I'm not gonna do this way. You know how I will do it? I will show you how I do it. Okay. So I have here 1 input this way. Okay. And now for every input here, I'm gonna add like for every input here, I'm gonna add something like a multiplexer, a small multiplexer. So for every input here, I'm gonna add like a multiplexer. This multiplexer is controlled by loads. Okay, and here I'm gonna have 2 inputs, either I0 or the old value. Okay, this is the old value or I0. So that when load equals 0, so I'm gonna connect the input here to the old value. The old value will be written again. Okay, or when load is equal to 1, so actually I'm gonna connect it to the new value so that you can write the new value. You got it? So here, what can we do? For every input here, I'm gonna add a multiplexer. Okay. In this multiplexer, load is has 2 inputs. 1 input comes from the old value. 1 input is gonna come from the load, or this is what is the new value I want to load here. Okay. And by the value of load, either I connect the old value or I connect this one here. Okay? How can you make this simple multiplexer? Okay, you can do this way. You know, in case of multiplexer, you need two ends here. So I can have two ends this way, and then they are going to connect it together using OR. Okay, and here I'm going to connect load. Here I'm going to connect load. Here I'm going to connect load prime. Okay? Load here select. You remember when you had select before S? It's the same thing. Here I can connect load and load prime. Okay. When I connect to load here, I'm going to connect E node. Here, I have to connect the old value, which is actually E node. So I'm going to put this one E node. You can see here from this small multiplexer, you can see when load is equal to 1, so this end is off, this one end is on, and the output here is going to be I node, and the output here is going to be I node. I node is the new value, the new number. So now you are enabling loading. Okay. When load equal to 0, this end is off. Again, this is a multiplexer. Okay. And this load prime is actually 1, and then I'm gonna get E node, and then I will get again E node. This input, remember, this input will come here. Okay, guys. Again, if I ask a question, so I will show you, yeah, this is how it works. So here for every input, so this circuit is similar to this circuit. All what I did, as I told you, I added here for every input, I added a multiplexer, okay, controlled by load. And that's what I did here. You see, for every input, here, I'm gonna connect here load prime, because it's coming from here, load prime. Here, I'm gonna connect load. When I connect to load, I'm gonna connect I node. Okay. When I connect to load prime, I'm gonna connect E node, as you see here, E node here. Okay. So that based on the value of load, if load is equal to 0, E node will be here. So it's like you are gonna connect E node again. You are receiving no change. Okay. But if load is equal to 1, so this one is off. Okay. So here it's gonna come I node here, and whatever come here, this will be the new value. This is D flip. Okay, guys. So again, this one is similar to the previous one here, but just I added one more feature. The feature is enable. I added one bit here for enable. Okay. Again, in exam, I will not be specific, okay, because again, we are in the last week. I will not be specific. If you want to do this one, and this one is to me is easier, I'm totally fine. If you want to do this one also, I'm totally fine. I'm not going to ask you in exam if it has load or not. If you do any one of them, all what if I ask here in this part, I will just ask you to draw 3-bit, 4-bit, 5-bit, a certain number of bits. That's it. You do this one, okay. Do the other one. Okay. Any question? You understand what I mean by register? Okay. How we make it? We make it out of D flip-flops, as you see here. Okay. And why we use it? We use it a lot. So if you look at any microcontroller, microprocessor, if you look at any digital system, the system is full of registers. Okay? Because if you have arithmetic unit like other multiplier, what division, whatever system is, I need to store the output somewhere. Also, I need to store the input somewhere. That's why we use register. And register, again, it's like, again, guys, after you finish the course, too bad, okay? Flip-flop is a storage unit that store 1 bit. What is a register? Register is a storage unit that can store any bits. You have any bit register, it should have any flip-flops. Okay? Any shot. Okay. Now I'm going to move to the next device. We call it shift register. Also, when you teach, I used to teach 3130. 3130 is microcomputer systems, okay, which you teach assembly. I used to teach this course. I'm not teaching it now. So here in this course, when you see assembly, you will find, you know, assembly language. Every instruction you have in assembly language has a hardware that is executed. This is the main difference between high-level programming language and low-level programming language. low-level programming language like assembly, every instruction you have is going to be executed by the hardware. There is hardware that support. Okay, so when you keep this course, you remember me when the instructor teach you shift register, shift instruction. So we have some instructions to do shift. And you will understand how we can do this. Okay, but here I'm gonna only focus on the hardware.
I'm gonna show how the hardware can shift.
When you go to this course, you will see how the software can do shift and how to use it. You understand what I'm saying? Anyway, so let's see what you mean by shift register. Okay, again, now we have two words. One word register and one word shift. We already know what is register. So register is a storage unit that will store units. Okay, so how this one is different from this one here? How I already taught to us register. So how shift register is different? Okay? Very simple. This is a register that is storing any bits. Okay? However, I can shift this any bits. I can shift it. What do you mean by shift? That's what I'm gonna explain. Okay? So here, shift means this one here, I can't shift. If I'm storing a number, so yeah, so it will be this number. I can't shift it. This one is a register. Yes, you are storing a number, but I have the capability to shift this number. Okay? We need this operation in digital computer. Any digital system will need this kind of shift. When you take this course, you will understand how we use shift. Okay? But here I'm teaching the hardware aspect of it. Hardware aspect means how the hardware can do shift. Okay? So let's define what I mean by shift. So if you have here a 4-bit shift register, again 4-bit means it's a register that is storing 4 bits, as you see here. Okay. Again, we have a clock input. Okay. On top of that, we have serial input and serial output. Okay. Here I want to explain what I mean by shift. Okay, this is a register. It's storing 4 bits. Totally fine. But I can shift these 4 bits. What do you mean by shift? That's what I'm explaining now. Okay? Shift means, look here, guys. It means you can tell from the screen. Shift. Okay? So we have to do it here.
If you look at this row,
And then I
shift from here.
what shift means? That means this student will move to the next position. This one here is going to move to the next position. And you are going to move to the next position. And so on. That's exactly what we are doing. You got what I'm saying? So every bit is going to be shifted to the next position. So as you see here, for example, here in the serial input, if I input one here in the serial input, okay, as you see here, when the clock comes, every bit is shifted. That means what it means? It means this bit is going to be shifted one position. This was like bit number 1 or bit number 0, bit number 1, bit number 2, bit number 3. So bit number in the location number 3 is going to go to location number 2. The bit that's in location number 2 is going to go to location number 1. The bit as location number 1 is going to go to the bit location number 0. And the first one is gone, is lost. So here I'm going to lose. That's exactly what happened. I'm going to lose this bit. Every bit is going to shift it, and the new one will come to here. So this bit is going to come here. This bit is going to come here. This bit is going to come here. Okay. This bit, the old bit here is this one is lost, and then the new one will come. All of them will shift. What I'm saying? That's why if I input here 1, this is how it looks like. And in the
like we did the first bit here.
Okay. So every clock you do one shift. Every clock, every now what if I put the input? I put input 0 and then I shift again. So here you can see this one will move to one position. Here, this one is gonna come here. This 0 is gonna come here. This 0 is gonna come here. This 0 is gone. I'm gonna lose it. So every time I lose 1 bit and I add 1 bit. This is how it is. So every time I add 1 bit from the right, I add 1 bit. I lose 1 bit from. So this is from the left, my left. This is from the right. I'm gonna lose 1 bit from the right. I'm gonna add 1 bit to the left. And then every bit is going to be shifted to one position. Is that okay? So as you see here,
If it's zero, then you have
here, shift, we have the flush. Every bit is shifted, which one I get shift, and then you have Every time I input a new bit,
And then
I'm gonna get all of the serial output is the- So I need a hardware circuit to do. Don't ask me, or maybe when you go to the 3130, you'll understand how you are going to have an assembly instruction called shift. This instruction will do process here. It's a purpose of this course to show you how the hardware can do it. How this can be useful in the software, that's what you are going to do. But before I continue, here we have two types of shift. We have two types of this register. We have shift right and shift left. It depends on the direction. You can see here, you can see from what I explained in this example, you are shifting this way. Okay, because this is shift right.
shifting this way, shift right.
There is another hardware circuit I can make that shift it this way. We call it shift left. You have two types of left. One hardware that shifts this way.
Or this is my left hand, shift is this way, one shift left. Shift is this way, or this right hand, shift right.
So we have two hardware circuits. That's okay. So now, I think I have another. Yeah, that's what I'm explaining here. If you shift this way, we call it shift right. If you shift this way, it's called shift left. I'm explaining here in case you shift right. A bit, one bit enter to the most significant bit. Shift right. One bit here to the most significant bit. And then you are going to lose. This significant bit is going to be lost. Here is the opposite. Here, input will be from here. So I'm going to input one bit here from the less significant bit. And actually the most significant bit will be lost. And every clock. So this shift, every clock, you got what I'm saying? Every time there is rising, there is a shift. Okay. Now, how can you use it? Very simple. Very simple. Look. The way I can do it, for example, if I want to have 4-bit shift right register. Okay. So 4-bit means I need four flip-flops, as you see here. I have 4 flip-flops this way. Okay? This is the number. A0 is the number stored by this flip-flop. A1 is the number stored by this flip-flop. A2 is the number stored by this flip. The A3 is the number stored by this flip-flop. All of them have the same clock. It's very easy. Why is it very easy? Look how it works. When you have a clock here, what happens when you have a clock? Yeah, any D flip-flop, whatever you have in the input here will come here. And A3 will come here. So this one will come A3. A2 will come here. This one will come here, and then the first one will lose. So what I did, I used four D flip-flop. The output of one of them is going to be output of one input to the other one. Because this is how D flip-flop works. The way D flip-flop works, whatever you have here in D is going to go to the output. Because that's how it works. Every time you have a clock. That's why every time you have a clock, you are going to shift by 1 bit. Clock, 1 bit. Clock, 1 bit. So every clock you shift only by 1 bit. Okay? Whatever you have here in this, that's why you have here serial input. We have here serial output. Okay. So whatever you have here, when there is a clock, okay, whatever you have here is gonna come to this bit. A3 is gonna come here. Because that's how this flip-flop works. That's why I'm telling you, it's very easy. I'm not going to teach you something big or something new in this chapter. I just use what we had before. Okay? E2 is going to come here. E1 is going to come here, and E0 is lost. Okay. Yeah, I make it here also in the table if you want to understand it. Initially, we had 0, 0, 0. Initially, if serial input is 1, so after one clock, this one will come here. This 0 come here, this 0 come here, this 0 come here, and the first 0 flip. Okay? Now, if I put the input is 1, and now I have a clock. Here, this one is going to be shifted, this 0 shifted, this 0 shifted, the first 0 I lose it, and this one will come here. Okay, guys? I can continue this. Any questions? It's not difficult. It's just I use what we had before. If you understand and we have how this flip-flop works, it should be easy. This is shift right. Can anybody tell me how I can modify this circuit to make it shift left? Yeah, just flip everyone. So that means this one should be serial input because I'm gonna input from here. This one should be serial output. This one should be D and this is Q. D, Q, D, Q, D, and this one is Q. By this way, whatever I have a D will come to Q. Whatever I have a D is gonna come to Q. Any questions about that? Okay. So there is also something here. I'm sure you maybe have some idea about it. It's about serial and parallel transmission of data. So if you have here, guys, when you in communication, we have two types, either serial communication or parallel. Okay. So I want you to understand the difference. In case of serial communication, like the USB serial, okay. Other things, when you teach microcontroller, you understand better. We have sometimes when we can communicate serial or parallel. I want you to understand the difference. Serial means, for example, if I want to transmit 8-bit data, my data is 8 bits.
Okay.
So the way here we have transmitter, here we have the receiver. For sure, we should have the same clock to be synchronized. Okay. And we have only one wire here, only one wire between us. Okay. And if the information, for example, I want to transmit is 1011 1100, something like that. What happens here, guys, is in serial communication, in one clock, I'm gonna put here 0 on the line. One clock. You take it. So imagine it. We have a line between transmitter and receiver. I'm gonna put the volt for one clock. You will take it. And then in the next clock, I'm gonna put 0. So again, then I'm gonna put here 1. And so on. In order to implement this idea, I need shift register. There should be shift right here, and there should be shift left here. How it works, I'm going to tell you how. For example, here you have a shift register to the right. Here you have shift register to right as well. Okay. So for example, if you have here 101 10001, any number. Okay. So then we have wire here. Okay. So what happens here after one clock, this I'm gonna put here 1, and then you are gonna input it here. Okay. And now we have 0 here. 0 is the next one. Another clock. I'm gonna put here 0, and then you are gonna shift this one. It becomes 0 and 1. Transferring the data serial, bit by bit. Okay. That means I need 8 clocks. After 8 clocks, because every clock I transmit 1 bit. After 8 clocks, I'm gonna transmit the 8 bits. Make sense? So here every 1 clock, I'm gonna output 1 from here. Every 1 clock, I'm gonna output 1 from here. Every 1 clock, you are gonna input 1. Make sense? Okay. In case of parallel is different. In case of parallel, here this is a transmitter, this is the receiver. We're gonna have 8, 1, 2, 3, 4, all the time until 8. We're gonna have 8 wires.
8 wires.
Okay. And what we can do is this number, I'm gonna output the number here. 1, whatever the number is, 0011, and then I need only 1 clock to transfer the 8 at once. Only 1 clock, I can transfer
the 8 at once.
What I'm saying? So instead of 8 clocks here, I need only one clock. You can notice this one for sure it's much faster, but it's more complicated because you need you need 8 wires. Okay. This one is still, although it is slow,
Still, it is
very useful. Sometimes you do need the very high speed. Okay? If you have a sensor, temperature sensor, and it's enough to connect it using serial. Okay, so that because you don't need this very high speed. Okay, sometimes depending on the application, I don't need this very high speed. Okay, so the temperature sensor, if I take the 8 bits using serial, it should be enough. Okay, so we have this one, and also we have this one as well. But I just want to talk about the rule of the registers here. If you see what I'm doing here, this is actually parallel load. So if I want it hardware, if I want to implement this idea using hardware, so here at the receiver here, there should be parallel load. So here I0 should be connected here. So I need to use this register here, this register. So these inputs, okay, I can read them. These inputs here are coming from the parallel here. Here I can use shift. So this is when you use shift bit by bit. Okay, guys. So usually communication in any computer system, either use serial or use parallel. I just wanna understand the rule of registers. If I have a parallel load, okay, so you can actually, I can write the 8 together using only one clock. Here I can use shift with this register. Any question? Because sometimes because the data, as I told you, the data usually I'm gonna receive it either serial or parallel. Sometimes I need to convert from parallel to serial or serial to parallel. Okay. Also, register can help me to do that. How? I'm gonna tell you how. For example, here, yeah, in this register here, guys, I'm gonna input. The input will come from here, serial, bit by bit. Input from here, serial. Okay. If I take the output from here, I'm gonna also take it serial. Okay. But if I take the output from here, I can take it parallel. So let me clarify what I said. What I said is, I wanna here I'm gonna input a number, something like 1011, a number like this one. Okay, it needs 4 clock because every clock, this one I'm gonna input 1 here, the first one here. Okay, next clock is gonna be 11. Next clock is gonna become 011. Next clock is gonna become 1011. Okay? So now I inputted this number serial, but now I can take it parallel from here. Sometimes I want to receive the data serial, but I want to send it parallel. So I need something like serial to parallel converter. This can do that. Make sense?
Yes.
So, we're doing assembly for the serial input. That's the bitwise logic. And parallel will be like correctly.
You mean assembly?
Yeah, something like.
Assembly, if you look in assembly language, you will find an instruction that is
Shift.
okay.
You have register A.
You have an instruction to shift the register to the right and to the left.
You have
This operation in assembly. This is how the hardware will do it. How here I'm explaining how can you use shift to do for communication, but also shift can be used for other things like bit manipulation. If you want to manipulate some bits, and that's what we are going to teach. You understand what I'm saying? You want to manipulate some bits for bit manipulations, another way to do it. Okay? But here I want to focus on the hardware aspect of it, and then when you go to 3130 and you took instruction shift right, shift left, you know how the hardware can do it. But every instruction you have in assembly, it's supported by hardware. It's going to be executed directly by the hardware. Any questions? So now I explain how can you make the circuit that you can shift right or shift left. There is also another instruction. Also, you will learn in assembly how it is important, how it is you can use it. We call it rotate instead of shift, rotate. Also, we have rotate right, rotate left. Okay, so you can tell again. You can tell rotate. This is shift, this is rotate. Think about how the word shift in English is different from the word rotate. Okay? So again, we have, I explained how can we do shift right, shift left. Also, we have rotate right, rotate left. So you can see, again, it's very easy. That's why I'm telling you, yes, I'm teaching this chapter it's the last week, but nothing is new. Just use what I not something is. So here you can see, guys, this one here, circuit is just exactly similar to this circuit here for shift, But what I will do here, in case of rotate, there is no serial input. Okay, so then I'm gonna make a wire this way, connect this. That means I'm not gonna input a new bit. I'm gonna just rotate the bits like that. I'm gonna rotate them. That's it. That means the big difference between shift and rotate. Okay, in case of
shift,
I'm gonna lose this bit. Okay, every bit is shift. In case of rotate, I'm not gonna lose anything. This bit is gonna rotate back to the beginning again, and every shift is shifted by one. Yeah, and then I will take your question. So this is also one of the operation we use in hardware and assembly. Here I'm teaching how the hardware can do it. You need to understand. Nothing is new. All what I did, I just no new input. Okay, I just connected the output to the input. How it works? Look here. Here. Up every clock you rotate one bit. Every clock. Okay? So here in one clock, this bit here is gonna move to here, and this is the new number. One more clock. This bit is gonna come to here. No input. I'm not gonna input. I'm not gonna lose anything. Okay, just you wanna rotate the bits. Okay. Again, don't. Maybe it's too early to tell you how something like that is useful, but you use it in programming. We need something like that in programming to do something like that. Okay, I'm explaining here the hardware aspect of how hardware. When you go to 3130, you will see this assembly instruction. Hopefully, you can understand, or you should understand how it can be used in programming this rotate. Okay, you should know what rotate means, how hardware can support. Yes.
How do you get your initial bits if there's no input?
that's a very good question.
Because that's a very good. If it doesn't have any input in the beginning, so what you are going to rotate here? Actually, here we can add parallel load as well. So here to this circuit, I can add here something like parallel load. Okay, so that first of all, you are going to load a number in parallel load. Okay, I'm going to show you something like that right now, and then after I load a number, so this is just to rotate. Okay, but actually, that's a very good question. It can't. You're asking a very good question today. I'm very happy for that. Okay, so what I'm saying here is, yes, this is that's very smart. So how if there is no initial number, so how you are going to rotate it? Okay, because here I'm focusing only on rotate, but actually, if you want to use it, so you are gonna have two things. Parallel loop, you can parallel loop, and also you can rotate. Okay, so first I need to parallel loop the number, and then after that you can rotate. Okay. Any questions? I will show you how can we do something like that. Any questions? So again, guys, let me summarize what I said before I continue. Today I explained 4-bit register. What is register? Okay, I explained how can you add enable or load to the register. I explained a special type of a register. We call it shift register. Okay, where you store a number and you have two types of them: shift right and shift left. Same thing. We have here rotate. Rotate is like a special kind of shift. Rotate. We have here rotate right register. Also, you can have rotate left as well. Here, this one because you rotate this way. When you shift to the right, you rotate right. You can, in case of rotate left, it has to be this way. Okay. It has to be this way. Okay. How can you make it? It's very simple. Everything is the same, but this one has to be D, this one has to be Q. This one D, this one Q. This one D, this one Q. This one D, this one Q. Okay? And this time, this arrow has to be this way. Output here, input here. Pretty easy, right? Anyway, now again, guys, again, because we're in the last week, if I ask a question here, I'm not gonna ask about shift register. I'm not gonna ask about, oh, sorry. Because I already wrote the exam, but I already wrote in the, what exactly we need here. Okay? I don't remember if I asked it about shift register or not. But anyway, it's easy, right? Explain it here. But I already wrote in the exam, so I really I don't remember now, but they already told you. Okay. Anyway, I'm gonna leave this one for now. Okay, because I have more important things to teach than this one. If I have time at the end, I will come to here. Now, also this one for sure it's not gonna be in the exam, but it's related to your question. It's very interesting. So sometimes you can buy a chip. This is chip, we call it universal shift register. You have a chip, okay? It's very easy. So it's not going to be in the exam, but I just, I want to show how it works because it's going to put two
Next together, I
put in this course, okay? Like multiplexer with shift. So it's very easy, but let's see how, so you can buy a chip and this chip, it's called universal shift register. So what it means, look here guys, very easy. It means, for example, you have any bit input parallel. When you see something
that needs to go.
when I put like this way, put 4, that means something. So you have here 4 input for parallel loop, and you have 4 output this way. Okay. Also, this one universal. You will understand why it's universal because actually you can do shift left, you can do shift right, you can do parallel loop. You can do 3 things. Okay? Based on the selection here. You have 2 selection, 2 input selection here. If this selection is 0, 0, so actually no change. No change means if the register is storing 1, 1, 0, 0, it's gonna stay, it's gonna continue 1, 1, 0, 0. You are not gonna change the sort event. Is that okay? If I put here 0, 0 means no change. Okay. If you put here number 1, so that means I want to shift right. If I put here 1, 0, that means I want to shift left. If I put 1, 1, I want to do parallel load. Parallel load means whatever you have here is going to be written. Okay. That's why here I need, for sure I need clock. So I need clock. Also I have here 1 bit for clear. So this bit, if you put here 0, you are gonna clear. You are gonna clear all the flip flops you have here. On top of that, I need also serial in to the right, serial in to the left. One to the right, one to the left. Anyway, so how can I make something like that? One circuit with a selection. Okay. Again, it's easy, but it's just a little bit complicated. That's why I told you this one is not gonna be in the final exam. Okay. Look how I make it. Okay, guys. Believe me, it's very easy. Here, I'm gonna have a multiplexer, 4 multiplexers. Okay. This multiplexer, the output of this multiplexer is connected to every G, as you see here. And using the selection I have, I'm gonna select 1 of 4 inputs. Okay. Look at that. Very simple. I told you if the selection 0, 0, I want to make no change. Okay. So how can you make no change? Actually, if I just loop this one back, whatever I'm storing, I loop it back. And that's exactly how I wired it. So the way I wired it, so that if I put 0, 0 here, you are gonna connect to the first input. Okay, you are gonna connect it here. And I connected the first input to A3. What I'm saying? So using this multiplexer, when I put 0, 0, you actually are going to connect to the first input. In order to make no change, what I have to put here in the first input should be the current value. The value you are storing right. Make sense? That's why no change will happen. So if you have here 1, the 1 will come again. If you have here 0, the 0 will come again, and so on. Make sense? Okay. If I want to make 0, 1, so this one has to be 0, 1, it has to be shift right. So 0, 1, that means I'm going to connect to the input of the flip flops. I'm going to connect them to the second, to number 1, input number 1 here. So I'm going to wire input
number 1, so that you make shift right.
Okay. How? Look here, how I wired it. I wired it so that this one here, the input here has to come from this one. So that you shift from here to here. This one has to go to the next one. This one has to go to the next one. Very easy, right? And then the first one has to come from serial input. Okay. Now, if I make it 1, 0, so in this case, I want to make it shift left. Again, I know because this is a multiplexer. When you put in 1, 0, so I'm going to connect the input of each flip-flop to input number 2. So I'm going to wire input number 2 in such a way to make it shift left. How? Look here. This one has to come to the input of the second one here. This one has to come to the input of the second one here. This one has to come to the input of the second one here. And the first one here has to come from serial input. Okay. So I wire in such a way where this one has to be input here. This one has to be input here. This one has to be input here. And the first one has to come from serial input. Not one, okay, which is 1, 1. 1, 1 should be parallel loop. You know, because this is a multiplexer. 1, 1, I'm going to connect here the parallel loop this way. I'm going to connect input number 3 to the input of the flip-flop. Okay? So I'm going to wire it in such a way to make it parallel loop. How can I make that? Very easy. I have a parallel input. I'm going to connect it to number 3, number 3, number 3, number. Okay, guys, any questions? Anyway, this is not going to be in the exam. Again, is that this part is difficult? Register. So now I explain what is register. How can you make it using the flip-flop? I explain shift right, shift left registers. Okay, it's very easy. You see how I connected the circuit. The output of one flip-flop is input to the other one. Okay, rotate. Rotate is just a special case of shift. And now, sometimes you have a chip. This chip has a universal register. We call it universal register because you can connect it, you can make it shift right or shift left, or you can make it parallel loop. Okay? So in this case here, regarding your question, in this case, I can make it parallel loop.
And then I shift.
That's what I'm saying. By this way, I can convert the parallel
To serial.
anyway. Okay, guys, any questions? Now, now, guys, I'm gonna talk about counters. Okay. First of all, you remember in chapter 3 in sequence generator, how can you use sequential circuit to make counters? Is that okay? Counters are very useful in digital systems, and we use them all the time. Okay. Well, again, when you go to you will find your counters. Okay? Again, the benefit of this course is to teach the hardware aspect of how can you make counters using hardware. When you go there, you will focus your system. Okay. You will see how can I use the counter in many very useful engineering operations. Is that okay? But now, first of all, let's explain. So now I already explained how can we make counter. For example, if I go to, I already explained this. For example, counter is a sequential circuit. For example, I want to count 0. After 0 should be number 1. After number 1 should be number 2, and then number 3, and then go back here to continue this one. I already explained how can we make it. Okay. The purpose, what I'm going to teach now in these 2 types of counters is, I'm going to teach about. Okay, so here, you know, sequential circuit is difficult to do, right? It's
Like a very big counter.
so I see right now, how can I make it trick so that I can design the counter much easier than I don't need to do sequential circuit. You got what I'm saying? For sure, you can use sequential circuit, but
In big counter.
you need computation. I will show you how can I do some kind of magic. Okay, to design it much easier than sequential circuit. That's okay. You will do magic. Anyway. So, but first of all, let me explain to you, number 1, what we mean by counters. What counters is? Okay. So counters means it's a hardware circuit. For sure, you have block. Okay. For example, I can design 3-bit counters. I can design. I'm going to do something very small, like 3-bit counters. In case of 3-bit counters, I have 3 outputs this way. 3 outputs this way. Is that okay? The counter has to work this way, guys. Number one, the output I will get here in the very beginning is going to be 0, 0. Here, in general, I'm going to call it E0, E1, E2. Okay. And then after 1 clock, I'm going to have 0. After 1 clock, I'm going to move to the next state. You will see number 1. After 1 clock. After 1 clock, so every time there is, so every number here is going to stay for 1 clock. So every time there is a rising edge, you are going to move from one state to another. That's what we do in sequential circuit. In sequential circuit, every time there is a rising edge, you move from one state to another. So now 1 and then 2. After 1 clock, you will see here, if you see what number you have here, it's going to be number 2, 1, 2, 3, 4, 5, 6, 7. After 7, it's going to go back to 0 again. It's going to continue this way. All the way until 7 again. So as long as the counter is enabled, it's going to count from 0 to 7, then from 0 to 7, from 0 to 7, from 0 to 7, and so on. That's how it works. Any questions? Is that okay? And this kind of counter, we call it count up. You can tell from the English name, count up. Okay? We have another type of counter, we call it count down. Count down. So for count down, it's the same thing, but actually I'm going to start from number 7. After 7, it becomes 6, 7, then 6, then 5, then 4 until 0. After 0, you're going to go to 7. You got what I'm saying? So if you count up, I'm going to start from 0 to 7, and then 0 to 7, 0 to 7. You count up every clock. You are going to move from increment the counter by 1. Okay? So now you don't need to understand. Okay, how this? It looks like you are playing the game, or what? What is this? How can you use it? It's very useful. And our computer system is very useful. Okay? And it's not the benefit of this box. The benefit is to know what is counter, what counter means. How should we decide? How do we that's it. You understand? You only teach me what is counter. Okay, we can just use it. Okay? And the other one we have count down. In count down, you start from 7, 6, 5, 4 until 0, and then from 0 to 7 again, and so on. You repeat. As long as it is enabled, you are get every clock. So you move from here to here every clock. Any questions about what's counter? It's a sequential circuit, right? From one state to another state, another state, another state. And every time you move from one state to another, 1 clock. Any questions? Okay. Now, we have 2 types of these counters. Okay, that's what it's very easy. It's not going to be too complicated like the sequential circuit I explained. I will do a trick using this trick.
3-bit counter or 1 million bit counter. Because it's
okay. You don't need to, for sure, if you want to do it using sequential circuit, it will be too complicated.
Okay, it's too big.
But anyway, I'll show us. But anyway, but before I continue, we have 2 types of counters. One is called synchronous, and one is called rebel. Before I show you both of them, I want to show you what is the difference between both of them, rebel and synchronous. Also, without thinking, every time you see the word synchronous, it means all of them have the same clock. So what happens here in this counter, if you have 3-bit counter, so here you will see I'm going to use 3 flip-flops. Okay? So the number of flip-flops I'm using in the counter should equal to the number of bits. If I have
1 million bit counter, so I should have 1 million
flip-flops. Every flip-flop is going to store 1 bit, like a register. So here synchronous means all of them have the same clock. So all of them are going to be all of them connected to the same clock. This is the meaning of word synchronous. This is one way to design counter. Okay? There is another way, rebel. The word rebel means one flip-flop is going to trigger the next one. Next one is going to trigger the next one. You got what I'm saying? So here rebel means the clock of one flip-flop is coming from the previous flip-flop. Yeah. So they are not connected. You will see right now. Again. So there are 2 ways to design these counters. Okay. One way synchronous. All of them are connected to the same clock. Okay. The other way is rebel. Rebel means the clock is flip-flop, it's triggered, it's coming from the output of the previous flip-flop. The output of one flip-flop is gonna trigger the clock of the next. You'll understand.
But this is the main difference between them.
This is number two, as you see right now. Most of the time when we design counters, we like to use T flip-flop. T flip-flop. This is why, as you will see right now, we like to use T flip-flop because as you will see right now, in counters, when you count, we have either one of two cases. Either no change or you need to flip. And that's actually what T flip-flop is doing. If T is equal to 0, no change to the value. So you will see right now, when we count, every flip has to do one of two things, either no change or flip. Okay? And that's why we like to use T flip-flop, is because it's gonna help us to do that. When T is equal to 1, actually it's gonna flip. One more thing, as you know, if you have J T flip-flop, you can easily make it T flip-flop this way. If you connect the two inputs of J T, so it becomes now T flip-flop. Also, thing, can anybody remind? Yeah, G flip-flop. How can you make G flip-flop? How can you make it T flip-flop? I think you can connect.
Oh,
Yes,
you do the K, you do a not to the K instead of,
an inverter.
yeah.
No, because let me think. If I put here 0, it becomes 0, 0, and 0, 0, no changes. If I put here 1, so this one becomes 1, 1, and 1, 1 is together. I think what we are saying is how can you make JK G flip-flop? So by this way, I have to put inverter here to make it G flip-flop.
Yeah.
What I'm talking about now, because I need T flip-flop. Can use T flip-flop in counters. What I'm talking is if you have GK, how can you make it T flip-flop? You just tie them together this way. Is that okay? Because if your input here is 0, 0, 0, no change. And input here is T, right? If you have 1 here, anyway, 1, 1 is going to be 2. Anyway, so again, as you will see right now, okay, when I design this count, number 1, you know what counter means? I explain what counter means. Number 2, I explain design in 2 different ways, either synchronous or ribbon. Number 3, I told you I'm going to use T flip-flop to do it, but it's not going to be too complicated. There is a trick. Once you know the trick, you can do this.
So I'm checking.
So let's start with this is a timing diagram for 4-bit counter. Okay, look here, guys. In the very beginning, should have 0, 0, 0, number 0. Okay? After one clock, I should have number 1. Number 1, as you see here. Makes sense? This is because I'm gonna have number 1, I'm gonna show you the timing diagram for the count. This number. Number 2, you will find some trick here. We will find the trick. This trick will help me to design it. Okay. So this is how it should look like. Okay. Then here, after 1, you can see we change the number, we increment the number by 1 every clock. So now this one should be 0, 1, 0, 0, which is number 2. Makes sense? After 1 clock should be 1, 1, 0, 0, which is number 3. Okay? It has to be all the way until 15. 1, 1, 1, 1 until 15. After 15, it has to be 0, 0, 0, 0 to start counting over again. Makes sense? Again, this is how it should be. If I have a counter, it has to be something like that. Makes sense? Okay? Gonna start it from here and see what there is. How I can wire the surface to
Okay, let's see.
That's why I'm telling you it's interesting. Look. It's easy, it's not difficult. Look here, guys. What kind of observation you are gonna have here? Okay, look at the observation here, guys. Number 1, these are 4 flip-flops. A0, A1, A2, A3. I have 4 flip-flops. Let's look at one by one. Here, remember, I'm doing the rebel. Rebel means the clock of one flip-flop should come from the previous one. Okay? But anyway, let's look at the first flip-flop. The first flip-flop has to be triggered by the clock. In
Yes, sir.
synchronous, when I come to synchronous, this clock has to be connected to
Everybody, that's a different story. But
Yeah.
now,
the clock is connected to the first one. Okay. Let's see what is the relation between this one and this one. What is the relation? Look here, guys. How I should connect this flip flop in order to give me, when this is the input, how I connect the flip flop to give me this output. How I can do that? Guys, every age, what happens here? You toggle. So this one is toggling all the time. You got what I'm saying? So the way I have to wire this one is, I'm gonna have this flip flop. I'm gonna put one all the time because every clock has to toggle. That's how it is, right? So here, this flip flop, every clock has to toggle. Every clock has to toggle. Every clock has to toggle. And so, okay? So this clock is connected to the first flip flop, and then I'm gonna connect the T to one, and this clock is gonna come to. Make sense? This is how I can do the first one. So I need flip flop the toggle all the time. Okay, and I'm gonna connect the clock to this flip flop. Make sense? Okay. Let's look at the second one. When it toggles, you can see the second one is gonna toggle every time there is a falling edge in A0. Every time there is a falling edge, please toggle. Every time there is a falling edge, please toggle. If there is a falling edge here, please toggle. Easy. So what happens here, this one is gonna toggle all the time, still T is 1, toggle all the time, but the clock will come from E0. The clock is gonna come from E0. So that this one is gonna toggle every time there is a falling edge here. Okay? Again, look at this one here. E2. E2 has to toggle every time there is a falling edge in E1. So E2 has to toggle all the time, but its clock has to come from E1. Same thing, E3. E3 every time has to toggle every time there is a falling edge in E2. Again, what I did here, guys, this is the output I should get. And then I'm trying to find the trick to, I'm not gonna, then I will need to think how I connect the circuit in order to get this output. You got what I'm saying? So the way it has to be connected is, look here. Number one, in case of 4-bit counters, I need 4 flip-flops. The first flip-flop, okay, all of them are toggling all the time.
all of them are toggling.
So T is equal to 1. Okay? But for the first one here, I'm going to connect the clock. The clock will be connected to the first one. And the output here is actually A node. Make sense? Then this A node here is going to be the clock for the next one. And always T is 1. Make sense? And this is actually E1. E1 will be the clock for next one. T is 1. All the time it's toggling. Right? Same thing here is going to connect to another one, another one, another one, another one. If I tell you to design 1 million bit counter, can you do it? Right? I don't need to make a sequential circuit like that. I'm going to keep connecting this way. Right? So if this comes in exam, I will ask you, if this one comes in exam, I will ask you to draw this circuit here. Okay? That's difficult to do. You understand what I did? Okay. So in exams, you don't need to connect it this way. Okay. This is exactly what I said. Look here, guys. This is the first flip-flop. Here, T are connected together to 1. You don't need to make it this way in exam. You can just, in order to make it easy for you and easy for me, you can just make one. This is how you are gonna connect it, okay? But you don't need to make it this way. It can be easier. You just connect here 1. You connect 1. That's it. If you give me 1, 1, 1, if you repeat the ones, I will understand they are connected together. You understand what I'm saying? So all of them are toggling. Okay, all of them inputs is 1, and then the clock or counter here, the clock is gonna be input to the first one, and the output of this one is gonna be clock trigger the next one. The output of this one is gonna trigger next one. The output of this one trigger next one. If you have more, output of this one trigger next one. The output of this one trigger next one. Okay, very easy, right? And it's supported by this observation. You can see here. That's why it's called ripple. Ripple. Ripple means every flip flop is gonna trigger the next one. That's the meaning of ripple. Okay? Any questions? For sure, if you want, and you don't need an exam to do it, but usually it's a good idea to add a reset. So that initially, if I want to start from 0, 0, 0, I want to start counting from 0, 0, 0. So in the very beginning, I have to make sure I have to put 0 in the reset to initialize it. Okay. But again, in exams, if you don't put it, I don't care. What really I care about here is I'm going to look at the input. Is that all of them are ones or not? It's number one. Number two, I'm going to see here what is the clock. The first one clock has to come from triggered by the clock, but everyone else should be triggered by the previous one. Okay. Again, this is coming from the look here. This is observation here. This one has to toggle every time there is a falling edge from the clock. So this one has to be clocked to this one. A1 has to toggle every time there is a falling edge from A1. So this one has to trigger this one, and so on. Any questions? You guys? Difficult? Good. Now, also, one more thing here. If I want to count down instead of counting up, I want to count down. Same thing. I'm gonna draw. This is the final diagram, and then I will get observation. I will see how I should connect the flip flop to different. So look here, guys. If this is counting down, so I have to start from 1, 1, 1, which is number 15. After that should be 0, 1, 1, 1. So every clock, I'm gonna decrement by 1, and then number 13, number 12, all the way until 0, 0, 0. After 0, 0, it has to go to 15 again. Count. Okay, so the count has to change every clock. Now, let's see, because there is a very small difference. Very interesting, very interesting. There is a very small difference between this circuit and this circuit, between counting up and counting down. Let's see what is the small difference. Look here, guys. The small difference is that, again, I will have an observation here. In order to generate this signal from this signal, you can see here, that means this one has to toggle every falling edge has to toggle. Okay? Every time there is a falling edge here, this one has to toggle. Every time there is a falling edge here, this one has to toggle. Okay? So this one will be similar to this one here, similar to this one. Okay? But if you look, if this one is the clock of this one, look what happens here. This one has to toggle every time there is a rising edge. In order to get this one here, in order to get this signal. Okay? So if you go back to here, this one can fall. So this is look how very simple. If you toggle this one every time there is a rising, sorry, if there is a falling, you are gonna make count down. This one, sorry, count up. If I flip every time there is a rising, it's gonna be count down. That's it. Okay? Here what happens here, guys. Look, this is just an observation. I can see if this one toggle every time there is a rising here, so it will be, I can get this one. Same thing. If this one is a clock for this one, also it has to be this flip flop has to toggle every time there is rising. Okay. So again, only the first flip flop should toggle when there is falling from the clock. But everyone else has to toggle when there is rising, not falling. Okay? There is different from what we had here. What we have here, all of them are falling. Okay? Here, the first one has to toggle at falling, at rising, but everyone else, when there is rising. Here, but here this is falling, and then rising. Is that okay? How can we do this circuit? Very easy. So you have two ways to do it. One way is I can use the exact circuit like this one, but I can make this one. I can use different flip flops. So this one is falling. This one here, the clock is falling. This one I can make it rising. Yes, can be okay. Yeah? But usually we don't like to use different types of flip-flops, okay? So if I want to use the same flip-flop, okay? So what happens here, instead of taking this one from A node, I'm gonna take it from A node prime. Because if it is rising here, it's gonna be falling here. That's it. So here I'm gonna connect it this one from A1 prime, this one from A2 prime. That's it. So let me tell you the conclusion, guys, to finish this lecture. Very easy. Look here. If you want to count up, I'm gonna use this circuit where the clock is connected to A. Make sense? But if I want to count it down, instead of connecting this everyone here, the first one is okay. I'm not gonna change. But after that, this one has to come from A node prime. But I'm not gonna change the type. It's gonna be the same type here. Okay. Same thing here. This one is gonna come from A1, and that's exactly what I did here in this circuit. So as you see here, I'm gonna get it from Q prime, so that when this one is rising, this one will be falling. Okay. Any questions? Is that difficult? So again, if I ask here a question in exam, I'm not gonna to make it easy. I'm gonna make it only count up, okay, not count down. Same thing, I will ask you to draw a circuit. If there is no time in the diagram or anything, just I will ask you to draw a circuit of 3-bit rebel counter or synchron and also synchronous counter when I explain it next time. Okay, guys, thanks.
Yeah, I can put it.